Hi, my name is Anand. I am a researcher at Microsoft Research in Redmond. Today, I'll be providing an overview of the topic of graph learning. My hope is to convince you that graph learning is an impactful and exciting research area and to encourage you to check out the sessions on this topic in both ATC and OSDI this year. Speaking of papers on this topic, we have two very exciting sessions. At ATC, on Wednesday, July 14, we have a session on searching for tracks graphs. This is on track 2 and will happen from 10:30 in the morning to 12 noon. At OSDI, we'll have a session on graph embeddings and neural networks on Friday, July 16 from 10:15 to 11:30 a.m. Please note that all times are in PDT. Let me begin by describing what we mean by the term graph learning. Very broadly, graph learning refers to machine learning where the input to the learning is graph structure data or data that can be represented as graphs. You may wonder why anyone would want to learn on graph structured inputs. Well, it turns out that many real world data sets are graphs. The most obvious example of this are social networks such as Facebook and Twitter, which is made up of social graphs of users and their friends. Graphs need not be only about people. For example, knowledge graphs, an important part of semantic web, captures relations between entities such as events and situations and power most of the world's largest search engines today. Computer networks is a graph of network nodes such as nhosts, routers, middle boxes, etc. And so is the internet itself, a giant graph of everything connected. While all those I mentioned until now are very familiar examples, less familiar but highly important ones, such as biology and medicine, also show graph structure. For instance, disease discovery can be and is often modeled as a graph. There are many more examples, but I assume you get the gist. The power of graph lies in the fact that they can capture the rich and complex relations between the entities in all these domains. As a result, learning on graphs lead to better performance. Indeed, graph learning has already had significant impact in many domains. It has been shown to be successful in discovering chemical structures, classify diseases and predict side effects of drugs, and particle simulation in sciences. Graph learning has proved to have superior performance compared to existing tasks such as text classification, machine translation, and vision. Finally, we also have the use cases in knowledge graphs and programming languages and so on. Let us now take a look at what kind of learning tasks are possible using graph learning. Broadly speaking, graph learning enables three categories of tasks. The first one is node classification, where given an input graph, the goal is to predict labels for new or previously unknown nodes. A typical example here is in detecting malicious accounts and frauds. For example, given a graph with users and their banking accounts, a bank may want to detect if a new user is malicious. An interesting real-world use case here is by Uber, where they have used node classification to detect collusion among users and drivers in their network. That was interesting. The second task is edge prediction, which predicts the existence of links between nodes in the graph. Recommendation systems are typical examples here. Based on articles read by a user, graph learning can be used to predict possible articles that the user might like. Many of us have seen examples of search engines showing relevant topics based on a search term rather than just spitting out a bunch of matches for a given keyword. Edge prediction on knowledge graphs greatly improve the relevance of such recommendations. Finally, graph classification predicts labels for a complete input graph or a subgraph. These tasks are mostly used in sciences, for example, to predict if a drug would be a good treatment for a particular disease. How do you learn from these graph structured data? A typical machine learning workflow consists of a bunch of raw input data in the training phase. The data is converted to features using something called feature extraction, either using feature engineering or using learning, and the extracted features are used by various downstream tasks. Very similar to this, in graph learning, we have one or more graphs as inputs. We learn the features that can be used by downstream tasks. In short, in graph learning, we learn the representation of the graph. Therefore, when we use the term graph learning, we most commonly refer to graph representation learning. The goal of graph representation learning is to learn task-agnostic features, or commonly known as embeddings. Embeddings are representations of graph entities in low-dimensional embedding space that captures the relation between the entities in the original graph. For example, given an input graph, nodes in the graph can be mapped to a d-dimensional space. Here, vectors z of c and z of d are embeddings of node c and d, such that similarity of the embeddings zz and cd between the nodes indicate their similarity in the original graph, for example, in this case, proximity. If we can learn these embeddings, then we can enable all the tasks that we defined earlier. For example, node classification can assign the same label to nodes with similar embeddings. To learn the embeddings in graph learning, we define two functions: an encoding function that maps nodes to the embeddings, and the similarity function that measures how relationships in the embedding vector space maps to the relation in the original graph. Then graph learning boils down to optimizing the parameters of encoder such that the similarity of the generated embeddings given by their dot product closely matches the similarity of the input. All graph learning architectures differ in how they define the encoding and how the similarity function is defined. Let's talk a little bit more about these. The simplest encoder is something called a shallow encoder, which is simply a lookup. Suppose we learn an embedding matrix called Z, which contains the node embeddings of all nodes. Then the shallow encoder simply retrieves a column in this matrix. To learn Z, we define an optimization problem which maximizes the dot product of embeddings for every pair of nodes that are similar. Such an encoder has many desirable properties. First of all, it's very simple, right? And consequently, it is very widely used today. Many shallow encoders exist today, but the techniques differ in how they define similarity. For example, deep walk uses the probability that two nodes co-occur on a random walk as a similarity metric, while dist mult, which is a different technique, uses cosine similarity. Second, shallow encoders directly optimize the embedding for each node so that every embedding is unique and nothing is shared. This makes them relatively easy to compute. However, there are disadvantages too. For instance, they are inherently transdective, which means that to generate an embedding, a node must be present at the time of training. Otherwise, you cannot do it. Further, they are unable to leverage the rich metadata associated with nodes in real-world graphs, which are quite useful. Due to these shortcomings, a new kind of encoders called deep encoders have been proposed not too long back. The idea here is that instead of being a simple lookup, the encoder can be a series of nonlinear transformations on the graph. That is, similar to existing deep learning, we can combine convolutions and neural network transformations to generate these embeddings. Graph learning, which uses such deep encoders, are known as graph neural networks, or GNNs today. In contrast to the shallow encoders, deep encoders, or GNNs, combine two things to learn the embeddings. First, they use the structure of the graph to determine what information to use in embeddings. As an example, to create an embedding for node A, a GNN may use information from its two-hop neighborhood. Second, they use a neural network to determine how the neighborhood information is transformed. Using these two, they create the computation graph or model for a node, which can then be trained to generate the embedding. GNN models are typically organized as a stack of two or more layers. The input to the first layer, or layer 0, is the raw feature vectors associated with the nodes in them. Today, there are many GNN architectures, and they differ on how they define and utilize the structure and transformations. Deep encoders use existing deep learning to train embeddings, as I mentioned earlier. Recall that we are interested in learning Z of V, or the embedding of a node after L layers of transformation. We just said that the input to the first layer, or layer 0 of the node, is the node feature itself. At any intermediate layer, we can compute the embedding C. by adding up our own embedding and that of our neighbors from the layer before us, and then finally passing it through a non-linear transformation such as ReLU. Now, this is similar to traditional deep learning, where the weight parameters W of L and B of L can be obtained by training the neural network with a loss function. Each node's embedding computation graph is defined, and then they can all be trained together. There are many advantages to deep encoding compared to shallow encoding. Every layer shares the same neural network and the weight parameters. As a result, deep encoders are called injective instead of transjective, which means that they can generalize to unseen nodes or graphs. Further, they can also use notch features, unlike shallow encoders, which result in better performance. Graph learning is a very active area of research with interdisciplinary nature. It is one of the fastest growing sub-areas in machine learning and has started becoming popular in systems and networking community. The reason why graph learning has invoked interest in the systems community is twofold. Due to their success in many domains, there is now a demand to apply graph learning to large graph inputs. Graphs with billions of nodes and trillions of edges are very common in industry. Second, graph learning architectures have started becoming increasingly sophisticated and complex. This has opened up several opportunities for us in the systems and networking community. Here is a brief sampling of some of the most pressing systems challenges in graph learning. Scalability is one of the big focus area in current graph learning research. How do we handle data sets that are huge? How do we deal with the fact that the real world graph keeps changing? And a complementary area to this is the efficiency of learning. When we train on large graphs, deep learning is supposed to be resource hungry, right? So how do we do cost-effective learning on graphs? Scheduling, data placement, data movement are all possible solutions to look at. Finally, security is another hard challenge, especially in graph learning, because of the sensitive nature of the data in many of these domains that I mentioned. Here, how do we make sure of the robustness against attacks in graph neural networks or graph learning? In short, I believe that this is an exciting time to be doing research in systems aspect of graph learning. At ATC and OSDI, we have 5 excellent papers that look at systems issues in graph learning. The first one is going to be presented at ATC on July 14th. Here, the authors look at the problem of scaling deep encoders. They observe that today, techniques move large amounts of data from storage to host memory, and that this results in large latency and power usage. The paper then asks a simple question: why not avoid data movement at all? Based on this, they propose an accelerator inside storage and show that you can speed up graph learning by an order of magnitude, which is excellent. The second paper will be presented at OSDI. Here, the authors tackle the problem of high cost of training due to graphs being larger and also due to the use of GPUs, which are very costly to hire in cloud settings. They observed that the training process can be decomposed into fine-grained tasks such that they can be trained efficiently on a combination of CPU-only machines and serverless threads. This completely avoids GPUs, but still gets performance on par or even better than using GPUs. The third paper focuses on existing graph learning frameworks and observed that they do same optimization techniques for all training methods, regardless of what the architecture is. This leads to poor utilization and performance, especially when the architecture are constantly evolving due to the involvement in the machine learning community. Towards this, they propose an efficient runtime that exploits the characteristics of both the learning architecture and the input graph. This leads to significant improvement in utilization and performance. The fourth paper focuses on shallow encoding compared to deep encoding in all the other papers, and observe that current systems that are used for knowledge graph embeddings are bottlenecked by data movement. This is in line with the observation made by the first paper, list that will be presented at ATC. They propose a novel way of reducing disk access and combine it with pipelining the I/O and computation to solve this problem. Using their technique, they show that it's possible to train a billion-edge graph on a single machine. The final paper focuses on distributed training of graph learning on multiple GPUs. They observed that although existing systems use the best techniques from both graph processing and distributed deep learning, they still exhibit poor scalability due to the need for communication. They go on to design a hybrid training approach that reduces the communication need significantly and improves training performance by up to 7x while scaling to multiple billions of edges. To summarize, graph learning is an emerging field with active research in machine learning, systems, and networking areas. It has already had significant impact in many domains and continue to be used in new settings. As systems researchers, we have significant opportunities in this space. There is a lot of interest in the industry. There are many open system challenges. This year, we have 5 amazing papers at ATC and OSDI that look at some of these issues. I hope you will check them out.